Right, so obviously, hopefully you all know me by now. I'm Jason Taylor. Going to be taking you through a few things today. So I'd say the first part of today's session is basically taking you through a little bit about theory of digital fabrication, just some tips and tricks about how 3D printers work, laser cutters, CNC machines, some tips and tricks on how to process your files for all of those as well. And then the second half of the session is a bit more of a live exercise, where we'll be downloading some files that I've put on our Moodle page. I'll show you where they are in a bit. And we're going to look through those systematically on how you can go about fixing your files and how you can start producing physical models from them. So there's little bits and pieces I've picked up over the last 20, 25 years or so of trying to 3D print and CNC and stuff like that. So, digital fabrication. Firstly, just show of hands, how many people here have made physical models before? Most of you, good. And how many of you have explored like advanced processes, like 3D printing, for instance? A few of you. Who would like to be able to 3D print? Most of you. Good, you're in the right place. So, first thing I'm going to look at, well, there's a few things we'll talk through today. So there's a few contents here. We're going to look at types of architectural model. We're going to look at additive and subtractive manufacture, look at some best practice and considerations, internal and external facilities that you have access to, some of which are free, some of which are not. And then, again, we'll move into like the live exercise straight after, how to prepare your files for 3D print, laser cut, CNC. So, three main types of model. So you got concept design model. So this is like kind of helping you with the design process. We usually call these like sketch models. Might be made of paper, you might crumple them up, get ideas for exploring forms. It's something that helps you with that initial design phase. You then get a working design model. This is where you typically have a design fleshed out, and then you're creating your model to help you rationalize that space, make sure it actually works in 3 dimensions, because obviously 3D digital models can be misleading. Things might look right, but people might forget to add doors and windows and stuff like that, right? And then, of course, lastly, we have a concept presentation model. So 3 different types of model. Now, the reason I start with these, and believe me, there are 100-odd different types of actual model, which we'll talk about. But the reason I start with these is because I think it's really important to stress that concept design models or sketch models, typically you would never 3D print for these. Yeah, it's a waste of plastic. And I think, as architectural designers, we're trying to reduce our carbon footprint, reduce the amount of plastic we're using, the amount of energy we consume. Sketch models should be analog. Work with your hands, make some stuff. And I say this as someone with bad hands. I have bad nerves in my hands. And I still make sketch models. So there's no excuse. Again, working design models might be a bit of a hybrid of the two. So it might be a mixture of some analog stuff as well as working with 3D printers, lasers, and CNCs. Typically for working design models, you'd be using like scrap materials and reclaimed timber, things like that. You'll know that both Scott and Pete have like a bank of like scrap materials you can work with. And then of course for concept presentation models or final models, you would obviously use the best materials you can find, the cleanest processes. These are the ones where you typically spend out a bit of money. So, in fact, before I go to that, why do we make models? Can anyone tell me? What is the point of a model? Yes.
General idea of things.
To get a general idea of things, yeah.
See how the space is evolved or how it's spatially designed.
See how it's spatially designed, yeah. Anything else? Any idea what they could maybe represent? Realistically, yeah, scale. Realistically, it all comes down to communication. So the types of models here, all of these have a complete different purpose. So for instance, we've got a topographic model where we're looking at kind of landscapes. Maybe it's like analyzing a site survey, for instance. Maybe I'm going to do some projection mapping onto this to see maps and how people circulate. We can do all that sort of stuff. We might want to just be conveying the exterior design or the interior design. We might want to be looking at the landscape design if you're a landscape architect. Do we have any landscape students here? None today, but there might be some online or watching this back on YouTube, so this is for you guys. A site model, I'll say this is the common one that we see in our school. we always see lots of site models for some reason. Site models aren't the be-all and end-all of architectural models. You can make other types of models. But, you know, I think with a site model, a good way to go about these would be to have like your existing context all in one material or one color, and then your design proposal, something similar to this, would be like in higher resolution or in like a better premium color or material. Something that shows an element of contrast to say, this is what it was, this is what I've made. And again, it's about kind of controlling the narrative. It's about controlling the way your viewer or your tutor or your client looks at your model and understands that relationship with it. Again, we've got things like urban design. Urban design's a more interesting one. It's very similar to a site model, but typically much higher resolution. And this is where you'd have a lot more detail. So, for instance, you might have little scale people walking around, interacting with the spaces. You might have some lights inside buildings to show a sense of like almost atmosphere within the model. There's a lot of things you can do. Had a student last year who won the B15 Architectural Model Making Award. He made this really nice structure. It's like a tensile kind of structure. And again, structural models. Being able to test that your buildings actually work on a smaller scale. An actual scaled structural model. So useful. Who here is rubbish at Grasshopper? I'm about here at the minute. I've lost my skills a little. So again, you know, if you didn't want to learn how to use Ladybug to do structural simulations or Honeybee for energy simulations, think of what you could do with your physical models. You know, if you're modeling them accurately to the way they'd be constructed at 1-to-1, just apply a scaled force to them and you're doing structural testing. So again, there's actual physical purposes to these. And then we get into the weird and wonderful. We get conceptual and abstract models. So conceptual, obviously explaining a concept. Abstract models, these don't have to be a particular scale. They don't have to be a particular material. They could be more about representing an idea or a process or something like that. So again, there's so many ways you can go about making a model. So next time your project brief says, make a model, think of this. Because you don't just have to make a site model and be boring. Do something weird and wonderful. And I love this abstract one here, where they've taken a book, they've laser cut all of the pages, and then they've stuck together the negative, which is this little block just there to the left. And you can see, that's the positive, and then you see the negative recessed into the book on the right. And again, the way that they've created that layering, absolutely stunning. To create a library out of a book. Oh, how cool is that? For anyone who hasn't seen this, this is still on display down at B15, this model. Highly recommend you check it out in the display case there. Can't remember if it's the first or second floor. One of the floors. I'm going to say first floor. And of course, construction details. Construction details to scale are always useful. Because again, it helps us to understand and rationalize and manipulate an actual construction detail. Make sure we understand how that physically works. So, what is the point? Now, before I go to that, what is the point of a model? Now that we've looked at this, who can tell me? Why do we make a model? You've kind of answered it already, most of you. To convey an idea, to represent scale, materiality. There's a lot of things it could represent, right? There's a lot of reasons why we might want to do it. Might want to do it to save time. Again, trying to set up a simulation for a structural test, that might take you 2 or 3 days. But maybe making a simple model to communicate that structure might take you an afternoon. So sometimes models can be faster than actually prototyping it digitally. Obviously, the benefit of doing it digitally is that you're not wasting materials and destroying the environment. So there's always a trade-off. Oh, and the other thing to mention is obviously the scales. So I don't know if anyone wants to take a picture of this. This will be uploaded on YouTube once we finally get around to processing all the videos. We are a couple of weeks behind with them. They're almost done, I promise. But again, you know, something like these, like if you're looking at a structural model, that's going to be like 1-to-20 to maybe 1-to-100, depending on the scale of the structure. A construction detail might be 1-to-5 to 1-to-20. Whereas at the opposite end of the scale, if you're doing like a topographic model, that could be all the way up to 1 to 10,000 scale. Absolutely massive. Or tiny, depending on the way you look at it. So again, something to consider. So what's the point? So firstly, it comes down to what you're trying to convey. And sorry if I'm teaching you to suck eggs with this. I'm sure you understand most of this already. But it's good to go back and rethink about these things, I think. It's so easy to get stuck in a rut and just think, okay, model means site model. So what are you trying to convey? Is it a new concept in its surrounding context? In which case, maybe a site model or an urban planning model might be appropriate. Are you trying to show a relationship to the construction method? Is your focus on the materials and processes being used? Maybe you're showing the circulation of the space. Or could it simply be for iterative form finding? Again, all of these factors should influence why you choose your materials, your scale, your construction methods. Scale and level of detail. Again, what is it that you're trying to represent? You know, if I'm trying to represent people walking around a site, for instance, something relatively small, I'm not going to be doing a 1 to 10,000 model. The 1 to 10,000, how high is a person going to be? I don't know if anyone wants to get out a calculator, but I'm about 170 high, 170 centimeters, 1700 millimeters. Divide that by 10,000, and that's how high I would be on a model. So something like that, tiny. You're not going to see it. So again, think about what you would represent at those levels of detail. So rule of thumb is the higher the scale, or the smaller the scale, so higher the number, like 1 to 10,000, the less detail you see. Makes sense. For instance, if you wanted to see a door or window details on a 1 to 50 scale model, that would be appropriate. But trying to do the same things on a 1 to 500 scale model, they would be absolutely tiny. You wouldn't see them. And of course the aesthetics. Everyone wants their model to look good. There's nothing worse than spending so much time making a model and having it be ugly. So again, something to consider is the aesthetic style. You know, would laser cutting the model actually ruin the style by having little scorch marks? Do you want to take the time to finely sand those little scorch marks off? Maybe 3D printing it might seem like a good idea, but if you're opting for a cheap method of 3D printing, where you get the little stepped layer lines, which we'll talk about, again, that can actually greatly ruin an aesthetic, as opposed to spending maybe £10 and going for a better process. So again, these are all things to consider. So now we've moved past the boring bit. We're going to be on to some slightly more boring bits, but hopefully useful boring bits. So who can tell me what additive and subtractive manufacture are? Has anyone heard these terms before? Jakey boy.
Adding materials or subtracting materials.
Exactly, that's all it is. Adding materials or subtracting materials. So additive manufacture is typically where you start usually from nothing and you layer materials up. So for instance, it could be that you're combining maybe like layers of laser cut material to make a topographic map. It could be that you're 3D printing stuff into layers to make a 3D printed object, where it's extruding plastic and adding over time. Or if you're using subtractive, again, that could also be laser cutting, because you can etch away, you can cut away. But it could also be things like CNC machining, water jet cutting, it could be any of these processes. So adding and removing material is all this is. So laser cutting typically looks something like this. Again, I'm sure most of you have explored a bit of laser cutting, either here or in another institution. But essentially the way this works is just using a little beam of light, a highly concentrated beam of light, a little laser, and it's just tracing your vectors, because you need vector geometry for this. And it'll trace your vectors and it'll be able to cut through most materials. Now, the printers we have here are Universal Laser Systems devices. They're really good ones. And with these, you can cut through most things. So things like perspex and acrylic, different types of card, even some really thin sheet metals you can cut through if you are Scott really nicely. But the great thing with these is you can also use them for etching and engraving, which are two different things. So typically you would have like a line engrave where it might trace like an outline of some text or something like that. Whereas etching would actually create like a relief. And in fact, I will skip to this one to show an example. So these are all 2D processes. There's nothing 3D about this, but you can produce 3D physical models with 2D data. So something like this I think is really useful. We can see how this is laser cut, maybe like a facade panel or a detail on the left. It's laser etched or engraved, I should say, like this same pattern on the middle one. That's just into leather, because you can etch and cut into leather. And then this etched one on the right is really interesting. And essentially the way this works, it works with grayscale. So if I had an image of this eagle in this ring on the right, very American and patriotic, which seems apt for today, Trump winning the election and all that. I'm very upset, I must say. I'm going to put that out there now. But the way this would work is anything that's white wouldn't etch at all. Anything that's black would etch to 100% depth. Anything that's a shade of grey between those values will etch to a different depth. And it can create this 3D relief kind of effect. And you can get some really stunning models out of this. I've done entire 3D reliefs of faces and things just by running the same pass multiple times, and it will create a full 3D map. Lovely way to do it. And that's something we don't see often in the school. So if you want to stand out at degree show time, do some cool stuff like this. Black and white image, set it to laser cut, you get yourself a physical model. Great stuff. Now, I don't know if anyone wants to take any pictures of these here. Again, I will be uploading this to YouTube, so you can rip it there as well. But there are some good best practice things to follow. So for instance, when you're laser cutting, the laser head is going to follow the lines of your vectors. So that means that if you have any duplicate objects, let's say I have the same line in the same place 10 times, that is going to cut over that same line 10 times. And that's where you get like uneven scorch marks across your models. So that's something to really consider. Same thing with etching and engraving as well. If you don't remove duplicates, you end up with like uneven elements. We recommend you work with lines, polylines, and arcs. So AutoCAD geometry, Revit geometry, Rhino geometry, all of these would generally work quite well. When you're transferring your files, we recommend saving these as a 2007 DXF. Now, most people at the university would disagree with me on that. They'll say, oh, export it to this one weird specific niche version. No, do it to this. I have been doing this for, again, 25 years. I've worked with about 350 different companies for laser cutting, CNC, etc. This is the one that always works with every single company. This is the one you use. So 2007 DXF, it works on everything. And you can export from almost all software in that format. The colors, again, might be slightly different depending on the machines. But if you're color coding your geometry, you can set it so that red lines will cut, blue will do a vector engrave, and black filled in objects, like hatched objects, would be like that etched relief, like what we saw on this one. Now, flatbed CNC. This is really similar to a laser cutter, except this time it's using what we call a mill bit. So I'm sure everyone's used a drill before, and everyone's familiar with like a drill bit. Looks really similar to that, but instead of cutting like downwards, it cuts sideways. So the blades are slightly different oriented. So it will kind of push into the wood, it will follow the vectors, and it will cut sideways, traveling along. And again, you can make small scale models from this, but you can make full scale one-to-one structures from this as well. So it's like a giant laser cutter in a way. It's a really, really nice process to have. Now again, in terms of best practice for this, it's very similar processes. So removing double lines, duplicated geometry, join your lines up where possible so it can follow them as continuous paths. If your lines aren't joint, sometimes the software will cut one line here, travel to the other side and cut a line, then travel back and cut another line. Whereas if your lines are joined, it will say, okay, I'm going to follow the path. It's going to go jum, 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 jum. It saves unnecessary travel time, which effectively reduces the speed of the job, means you get your parts quicker, uses less energy. It's just a nicer way to work. So join your geometry where you can. If you have closed geometry, let's say I have a perfect rectangle, something super basic. By having a closed geometry, that means I can set the path for cutting to be either on the curve, so the center of my milling piece is on the curve, or I can have it so it cuts inside or outside. So that's, again, something that's really worth knowing. Especially on something like this job here, where this might be like a 10 mil wide mill bit. You know, I could easily lose some tolerances here. If that's too wide, cutting inside or outside, that's a difference of 20 millimeters. That's huge. So knowing which side to cut is so important. Again, 2007 DXF also works for this. Now, things to be aware of. When you're using a milling machine, And this will be the same for 2D milling and 3D milling. Because it's basically using a mill bit instead of a beam of light, that cutting tool is cylindrical, yeah? It's round. And that means that if you have sharp corners, like in this bit, oh, hang on. If you have sharp corners like here, where you've got this round cutting tool, it's not going to be able to cut into those corners. So there's a couple of ways you could go about this. You could either leave it as it is and just let the mill bit do its job and leave those corners rounded. And then in the workshop, you would take a chisel and you would chisel those out to square them off. That's generally the cleanest way to do it. But if you're going for speed, if you're just going for like mass production or anything like that, you don't have time to chisel 500 corners on a complex model, then you might want to add little bunny ears. So something like these, if you can see them, it's a bit tricky to see. Essentially you place little circles just there that are the diameter of the mill bit, and it will just do a plunge cut on those corners to remove those pieces, but you end up with these little kind of bunny ear holes around it. So if you're doing like a big interlocking model, think like the Metropole Parasol, if you know that building. You might have seen it in like Seville, I believe it is, where you've got thousands of interlocking components. Something like that is what they would have done for that. Because again, it's going to save a lot of time. Now, last thing to mention with CNCs, you can also etch as well. It's not just a case of cutting. You can etch text, you can do all sorts of engraving. You can add different pieces onto it as well. They're not just rounded cylindrical pieces. You can also do like kind of 45-degree angle pieces. So you can do miter jointed components and stuff like that. It's great stuff. Now, this is definitely one to take a picture of. This is how to clean up pretty much any file in AutoCAD, because I'm not going to be showing you the AutoCAD method today. But there's a few commands here that are going to be really useful for removing duplicates, deleting constraints, all sorts of stuff. So in AutoCAD, the command overkill will become your best friend for this. It's the equivalent of doing like a cleaner version of a Make 2D in Rhino. I think everyone's taken a picture of that. Good. 3-axis CNC, and again, hopefully this is useful. I can see I'm losing some of you a little bit. 3-axis CNC works very much the same way, but instead of just working on the X and Y axis, it will also work on the Z axis as well. So it will work on the top layer, and it will take your 3D model, generate a toolpath from your 3D model, and it will just go along removing pieces of material, step down to the next layer, remove pieces of material. And typically you would do this in a couple of passes. So you'd start with like a wide mill bit first, to run across it fast to remove the bulk of material. We call this a rough cut, something like this. And then you might put a smaller mill bit on, or something a bit more detailed, and we would run across it again, like what this one's about to do, and we'd call this a finishing pass. And this would do 2 cuts, one to remove the bulk of material, one to then smooth it out, make it super, super clean. It's of course very, very messy, so the workshop technicians will be the ones operating the machines there. But again, great, great processes. If any of you have a laptop, chances are your laptops are probably CNC machined. This is how they would have been made, your laptop bodies, just out of blocks of aluminium. Now again, there's a few things here as well. There are some limitations. The key thing to consider here is that with a 3-axis CNC, it can cut left and right and back and forwards. It can plunge cut down, but it can't go underneath objects, because that cutting plunge is only straight up and down on the Z, yeah? So that means if I wanted to do things with overhangs, like if I'm cutting myself like this, I'm not cutting myself, but if I'm like this and I want to cut underneath my arm, that mill bit wouldn't be able to come and rotate and cut underneath. I'd have to flip myself upside down and cut from the other side. So there are some limitations to this. But these are fantastic for making molds in particular. So you can make these like final terrain and stuff like that you can make with these. You can mill foam, you can mill clay, you can mill wood, aluminium you can cut as well on this. But these are really good for making molds that you can then make replica and duplicate objects from. So a good example would be something like this. Again, limits that you have here, you're limited by the mill bit diameter and the mill bit depth. You can't do the undercuts, like I said, you'd have to flip the model upside down, or maybe multiple orientations. And you can only cut 2 opposite sides. So you can't cut from the top and the bottom and then flip it on the side, because then it would break what it's tied to. You need like a frame around it. You can create beautiful 3D reliefs, like this thing in the middle. That is CNC machined. I know that because that's one of my ones that I made. We've spray painted it white and photographed it. But again, I could then easily cast this. I could do like a silicon cast, replicate it, could do whatever I want with it. Mass produce. And again, the example of a mold there. This one is just a simple 2-part mold. So there's a bottom half and a top half, little locator pins, and I could do injection molded plastic for this. I could fill them with silicon, do whatever I want. Now, there are a few little file preppy bits here. Again, up to you if you want to take any pictures, but again, I will be sharing it. But there's a few things here that we would recommend you do if you're going to CNC. So there's things like trying to reduce your file size. Most CNC machines don't like overly complex models. So reducing the number of vertices in a model will help it process faster. Ensuring your geometry is closed and watertight is generally essential. Ensuring that all normals are facing the correct direction. And then saving as an STL, OBJ, or 3DS. Now, if you don't know what any of those things mean, don't worry. We'll get onto that on the live part of the session, which we're getting onto soon. And we'll actually explore what these issues are. Now, 3D printing, yay, starts getting a bit more interesting. So, as I said before, there are some various limits, similar to CNC with things like overhanging geometry, but the great thing with 3D printing is you can sell it to automatically build scaffolds and supports. So, I'm going to skip straight to the next slide on this. This has been put together by Print City, for anyone who knows what Print City is. If not, I'll explain in a minute. But there's some really good stuff just here. So essentially the way this works, it will take a completely empty bed, it will take your 3D model and it will slice it into layers. They're basically just images that it produces. And it will draw the outline of the image first by extruding plastic, then it will fill it in, the bed steps down by one layer, draws the outline of the next layer, fills it in, and it keeps doing it until you get a 3D object, just like this. Any overhanging objects, like we see over here on the right, it will build these little vertical supports, these little scaffolds that you would then break off afterwards. So it's a really, really nice way of making models, I would say. And nowadays the materials have become along so far that you can get all sorts of different types of materials. From PLA plastic, ABS plastic, to weird filaments like flexible materials, wood materials, magnetic materials, all sorts of stuff. You can do some seriously cool stuff with 3D printing. Now, this one in particular is what we call FDM, 3D printing, fused deposition modeling. And what this means is it's got a hot end, so the little extruder part of the 3D printer, and it's squeezing through this hot end, gets to about 190 to 230 degrees C, very hot, don't touch it. It will squeeze some plastic, typically PLA or ABS, and it will force it through this hot end, almost like a hot glue gun, but in a controlled manner based on those images it creates from the slicing. Some 3D printers will have multiple extruders. For instance, one can have like a water-soluble support, the other can have the plastic, which means that if you need that scaffold, you can print with the water-soluble scaffold, chuck it in water after, and that material just dissolves away to leave the final part. So you don't even need abrasive chemicals or anything. Now, the main limitation of FDM printing is this. As it creates the layers, it creates this kind of bulging at the sides, of each layer. Especially if you're printing in like a rough quality. Let's say it's the day before a deadline and you think, shit, I need a model for tomorrow, I didn't read the brief. Quick, whack something on the 3D printer. You could do that, and you could tell it to print in the fastest, roughest quality ever, but it's going to be really bumpy on the edge, it's going to look a bit nasty. Whereas if you're printing in something with a finer layer height, that means smaller layers, smaller bulges, cleaner surfaces. So again, something to consider. Also worth mentioning that if you're doing a structural model in particular, it will be weaker along those layers than it is on the other axes. So in this case, the Z axis would be the weakest compared to the X and Y. So just something to consider for structural models there. These are the FDM printers that you'll see at Print City. You'll be aware that we've got 4 of those in MTC here as well. The ones in MTC are completely free to use. So I basically stock it up with materials each year, leave them at the front. Either myself or Pete can induct you on how to put your files on the machine. You can just come along and print stuff. All we ask is that you use it reasonably. Don't print entire giant site models the size of this room and expect it to be for free. We're not about that. It's about you learning how to use the machines and gain a skill. If you want to print larger models or professional models, typically that's where you'd use a service like Print City, B15, the Make More facilities, or an external bureau. Now there's a bit here about material properties. Again, you got PLA plastic, which is very common, so widely recycled material, good adhesion, it's pretty strong, it's good for details, comes in just about any color you can imagine. So this is typically the material of choice. There are some material properties here, which are really good. So for instance, the ease of printing, that's got to be right up there, something that doesn't fail often. The amount of stress it can take and how well those layers stick together. That's why we like PLA. However, impact resistance is non-existent. If you drop it, it's probably going to shatter. If you try and stretch it, it's probably going to shatter. So it's not good for tensile models. ABS, on the other hand, does have some impact resistance. This plastic bin that you see in this room here, that'll probably be ABS plastic. Injection molded, but ABS. So it's a bit more industrial, and it requires a higher temperature to print, usually about 230, 240 degrees. Again, not as easy to print with, but it's heat resistant, it can do a lot of stuff, it's a really good material. PET, or PET, polyethylene, can't pronounce the second one. This one is food safe. So for anyone who wants to 3D print some little molds of things, maybe you want to make some little chocolates or something for Christmas, or some ice to go with your whiskey or whatever it might be. Again, you can do all of that. You can 3D print the molds out of PET, which is food safe, and you're not going to get any kind of plastic toxicity. So again, this is really cool stuff. Imagine at the degree show, having little miniature versions of your building that you've made as cakes or something like that, and being able to offer those out to employers. Be like, look what I made. Eat my project. You know, people are going to remember you for this stuff. So you can do some really cool stuff. Now, nylon's an interesting one. Nylon, I don't recommend you print on an FDM machine, like an extrusion type machine. It's not very good, if I'm honest. There's better processes for nylon. In fact, I've not included them in this presentation, but it's a type of printing called SLS or MJF. These are amazing. It basically uses like a laser to melt these plastic particles together. You get super high res, super strong materials. TPU, for those of you that want to do flexible stuff, TPU is by far the best thing you can use at the moment, I would say, for flexible objects. You can create gaskets for things, if you want to make something waterproof. You can make something rubbery or like silicon feet. You can create living hinges. You can do all that stuff with TPU on a free machine such as the Ultimakers. Absolutely fantastic stuff. So again, something to think about. You know, do you want people to come and interact with your models? Do you want people to actually be able to move and bend things around? Again, great material for it. I'm going to skip past that. I'm going to skip straight to the next machine, which is SLA. So you might have seen these. We do have them over in the space there that we've still not been allowed to set up because Bruntwood, who own the building, won't let us do it, even though they're completely safe to use. So I think what we're going to do, we're going to give these to Print City, and they're going to give us more Ultimakers. So you get more access to 3D printing, and you can still use those over there for free, but you just need to wait for them a bit. But typically these work slightly different. Instead of extruding plastic, this works as like a bed of resin. And again, it will take your layers, same way as before, divide them into, take your 3D files, divide them into layers. But what it will do, it will project an image on a screen of the layer, and it will cure that with UV light. So it's like a UV image that it projects. And that image sticks to the bed. Again, it can have supports as well. And as that bed retracts up, it breaks the adhesion with the bed below, comes back down into the resin, cures the next layer, breaks adhesion, comes back down, cures the next layer, and it keeps going until you get an object. And the great thing with this, you don't get the little layer lines, those little bulges on the side. You can do this in a range of different resins, some of which are transparent, some of which have really strong properties, some of which can be flexible as well. But what you get here is the resolution and the detail. These go down to like microns of detail. So if you want to do tiny scale people, scale furniture, tiny scale cars, this is the machine for that. The downside of this is it's more expensive than FDM printing. So typically for like a kilo of material on an FDM machine, it'd be about 15 to 20 pound. On here, it's closer to 40 pound. So you're looking at twice the cost of use of the other machine. Now again, there's a load of material properties here. You've got some that have like really high tensile strength. You have some that have more elongation at break. You have some that are really heat resistant. Each one has its own properties, so just let Print City know, or wherever you're going to print. Or you can buy your own machine and do it at home. I got 3 of these at home now because I'm sad. These SLA machines. What I would say, if you're going to do it at home, ventilation is key. This stuff is extremely toxic. If you put this in your bedroom and keep all the windows and doors closed, you won't be alive in the morning. You will die. And I do not say that lightly. We have had students end up in hospital in the past because they thought, oh wow, I'm going to get a 3D printer for £150 off eBay, which was fine. It's a good 3D printer, but they didn't ventilate the room. And you know, these are still toxic materials. You're playing with like material science and chemicals and stuff here. So you need to be really careful with this. And again, there's loads of stuff here. What I would recommend you do if you do decide to buy a 3D printer, or any machine for that matter, look at the materials that they use. Go to the website where they sell those materials, and you'll find something called an MSDS sheet, Material Safety Data Sheet. And it will tell you whether that material is toxic, what you should do in terms of handling it, should you wear specific types of gloves. For instance, for SLA, you need specifically nitrile gloves. You don't need to know this, but worth throwing it out there. If I were to use latex gloves, that material would eat straight through, absorb into my skin, and I'd get toxic quite quick. So you do need to be careful. Now, that's enough about the machines. We've got a little bit more about the models themselves. One thing I wanted to say is about combining processes. So I always thought this was quite an interesting one. We can see this is quite clearly a laser cut contoured model at the bottom. And then we've got a 3D printed kind of structure sitting on the top up here with little people. And then they probably just boxed the sides in, poured some resin, broke the sides off, and then I would have done a cleaner job personally of cutting those sides and polishing it up. So again, mixing processes adds so much more dimension to these models. For anyone who knows Anna in ADD, member of staff, this was her postgrad model that she did when she was studying down at Greenwich. This was a really interesting project. She 3D printed a mold for these waves that were hitting the Punta della Dogana in Italy, in Venice. And she embedded like little guns inside. It's all about the destruction of the waves on the site. So she embedded these guns within the resin. It's a very conceptual kind of model. But by combining laser cut, 3D print, mold making, she created something really interesting that won some awards. So again, something to think about. Maybe you don't want a 3D print at all. You know, you don't have to. You could simply just do, like wire bending, or maybe you just want to do like some 3D print for a structural reason. Something like this with wire bending, with little 3D printed clips, could be a great way to go about it. Just as like retaining things in place, structural elements. I know Danilo, the tech tutor, he does a module about teaching kind of smaller components and things, usually like for retention of components and stuff. Really, really nice way to go about it. Or maybe it's to 3D print this like, this kind of facade, I suppose it could be. Just figure out how you can mix processes. This is an interesting one. This is done in pieces. This is done purely on a CNC machine. So what they would do, you get blocks of reclaimed wood. This was actually from old tree stumps, this project, believe it or not. And they were taking these old destroyed tree stumps that were ripped up, taking 3D models that are divided into pieces. It looks like one big unified piece. It's actually segmented pieces. And they would mill these out and then slot them into place. And you can get really nice, interesting effects from it. Laser cut exterior, and then analog hand cut foam core interior. Again, doesn't have to always be digitally fabricated. Think about how you can mix those processes. I love that model. I'm going to go back to it. I just think that's such a clean model. Something really clean about that. This one's an interesting one. So with this, what they did, they made the mold and they poured concrete into the mold. I actually thought it was made a different way, but I'm told this is how they did it. They made a mold, poured concrete into the mold and broke that cast. They got the object out. And then they actually made the little person and stuff by hand. They actually sculpted them out of clay. I thought they were 3D printed. And then what they did, again, they boxed it off, poured resin, cleaned up the edges, squared them off, and then polished it up to get that transparency back. Really cool. This is the Metropole Parasol building I was talking about. You know when I was saying about the CNC with the little bunny ear cutouts? Imagine with an interlocking structure trying to chisel out all those corners. On a scale model version of that would take you forever. So obviously if you're doing it on a scale model, you would just laser cut to get the sharp corners. But if you were making a CNC model, plunge cutting those corners would save you, what, a week of time, easily, of cutting stuff. So again, stuff to consider. Now, just before we wrap that up and move on to the actual Rhino stuff, internal facilities you can access. You've got 3 main facilities. You've got B15 down at the UOM Humanities Building. You have Print City, which is a bit further than B15, but one of the largest 3D print bureaus in the UK. And again, they have a huge amount of machines and stuff you can access now. I'm talking a couple of hundred machines. And they only charge you cost of the materials. They don't charge you any fees on top. So cheaper than anything you'll find in practice. And then you also got Make More, which is over in the Chatham building on the ground floor. Again, there's an army of 3D printers there. And of course, I forgot to include the ones we have in MTC, our Ultimakers. You can also use those. It's actually 4 resources, not 3. Not bad. There's some information here for B15. Again, link to the B15 website. There's also a list of equipment that they have. So things like laser cutters, CNCs, 3D print, mold making and casting, vac forming, and traditional model making. All of that you can do at B15. You've got MMU Print City. Again, they have their own website. They are dedicated 3D print specialists. And we've actually just hired a GTA, a student assistant, who's going to be working with ADD and Print City to help clean up students' 3D files. They're going to be starting from next week, hopefully. So I can't announce who they are just yet. But as soon as we know, again, we'll publicise that and what have you. But what they can offer is FDM, so extrusion type, SLA, the resin type, but also things like DLP, SLS, PolyJet, and even things like reverse engineering with 3D scanning they can do. So again, some seriously cool stuff. And lastly, we have Make More, which again, CNC, laser, 3D print, traditional woodworking, casting, ceramics. They also do metalworking, they have welding facilities, you can do all sorts of stuff. So talk to any of the main technicians, and we recommend you do that early on in the project to work out the best way to go about modelling. But there's so many ways to engage with making. Now, if you're looking for something for like grad show level, like final presentation, the stuff that's going to get you the high paying jobs, get you a really cool job in practice, that sort of stuff, final presentation piece, you might want to print externally. Because you can imagine how busy all of the printers get during term time. Being able to 3D print externally means that you can get it within a specified time frame. Generally, as long as you allow about a week, you'll be able to get a part back in time. So the ones I recommend is Shapeways. Shapeways allow you to 3D print in like rare metals. So for instance, you can print in silver, gold, all sorts of stuff like that. Platinum, you can actually 3D print in platinum. The way they do it, they print in wax, cast it, do a lost wax process, melt the wax out, pour in the liquid metals, break that mold, and then you've got your finished object. That's the way they do that. But they send you really high quality pieces. If you want to do a giant model, again, send it to these guys, they can make giant models. The problem with Shapeways is they're not based in the UK, they're based overseas. So you're typically looking at an extra couple of days for things to come into the UK. Whenever I've used them, and I've used them a bunch in the past, I've usually had stuff within a week or 2. So not too bad. But obviously if you are printing in metals, that is a long process itself. That's 4 or 5 day process. So that you're not going to get in 3 days, for instance, because you can't make it in 3 days. 3D People are actually the company I recommend in the UK. It's actually led by one of my ex-students. He runs the company now. And he's fantastic. Their company's fantastic. Mention my name, you'll get a big discount. just saying. Like and subscribe, everyone online. Yeah, they'll sort you out. And they do that SLS and MJF nylon that I was saying about, and that's all they do. They don't do any other type. And what this gives you is really strong pieces in super high quality nylon, super smooth. It's great stuff. It's like final production level stuff. They look as good as injection molded pieces. So this is where you want pristine final level models. And they can do quite big models as well. There's a few do's and don'ts there just before we wrap up the presentation. So again, things that you should do. Talk to the technicians early on. Find out about the tool sizes, like the size of mill bits, dimensions of laser cutters, things like that. What are the limitations that are going to prevent you from making a model? What scale do you need to design to? Consider the model's purpose and function. How would that impact your decisions? And make sure that you're combining processes. The last thing we want to see is an entire site model that's been 3D printed in plastic. That is the worst thing you could ever present to a tutor, because that's an instant fail. Because it takes a lot of time, uses a lot of plastic, it looks shit, if I'm honest. Whereas if you're doing something a bit more ethically, combining a bit of laser cut, combining a bit of 3D print, some handcraft, it shows that you've thought about differentiating these materials and processes. It's a much better way to work. Things that you shouldn't do. Once you've justified the message that your model needs to convey, you should identify an appropriate scale to make it to. And again, that is where a lot of people go wrong. People are typically sending 1-to-1 scale files off to print and stuff like that, to SCART, to B15. They can't work with 1-to-1 scale files. You need to work out what scale to scale it down to, based on the machine size, the material size, the level of detail you want to represent. Work out what scale fits best. Work out whether there's any issues with your files. For instance, with 3D printing, you can't print anything thinner than 1mm on most machines. So if I have like a door, let's say, or maybe a wall, if that's 100mm in real life, 100mm thick, if I scale it down 1 to 100, that's 1mm, so that would be fine. If I change my scale, if I change that to 1 to 200, that's too thin to print. I'm going to get an invisible wall. And the other thing to consider as well, remember that scaffold I was saying about? If you're printing an entire building, let's say this building we're in now, this very room, if I went to 3D print this room, do I want to fill this entire room up with scaffold to hold this ceiling piece? No. That's firstly going to add a load of money, a load of material, and a load of stress trying to remove that material. If I separate the roof from my 3D model and print it in 2 pieces, it'll print twice as fast, be half the amount of material, and I can then not have to remove any support and just put the roof on top. So think about dividing your models up. So again, number of things there. Considerations: scale versus machine size, scale versus level of detail. And then the other thing we haven't spoken about is tolerance. Does anyone know what tolerance is?
Thickness of the nozzle, for example.
Yeah, exactly. So for instance, the thickness of the nozzle could be the width of the beam of light from the laser cutter. Essentially, what is the difference between your digital file to what you get in the end? So most 3D printers will have like a 0.1mm tolerance, most of them by standard. Some might be more, some might be less, depending on the process. But that means that if I'm making 2 pieces that interlock, and I'm going to do something really childish now, if I have something like that, if I have a hole and a shaft that needs to fit in, if I do those perfectly, the exact same size, say 10mm diameter, they're not going to fit. Even if I make that slightly bigger, it might not fit. I would have to work out what the tolerance is and make sure that my gap between the shaft and the hole is bigger than that tolerance. If they are, they'll fit like a glove. So just work out what the tolerance is for each process. Absolute final slide, I promise, is 3D to laser cut. For those of you that are Rhino users, there is a little link just here. Again, I am going to share this as a resource. If you want to automate any of your 3D models and turn them into laser cut models, this can do that. It's a little script that you can make yourself. Super easy, you don't need a plugin for it. But super basic Grasshopper script, and it will take any face, lay it flat. It can even automatically label and annotate parts, and it will lay them out onto a specified sheet size. It's really, really nice process, while reducing material wastage. It will optimally fit them. Really cool stuff. Oh God, that was a long presentation. I'm sure most of you have fallen asleep by now. Is anyone still with me? couple of you are still with me. Yay. Let me just check online, see how we're doing online. Ah, we've got lots of people online. Hello, online people. Hopefully you found that useful so far. Lots of stuff there. In fact, I think that's most of you. You've all joined online to see it on the second screen. It's all a lie. What we're going to do now, we're going to do something a bit more practical. So a bit of a live example. Hopefully you've all used some Rhino before. When we advertised the workshop, we did recommend you have some Rhino experience. If not, you'll probably still be able to follow along. But I made a little sample file for you to download. So what I recommend you do, go to the ADD Moodle page. Let's put this into student view. So on the student view, ADD Moodle page, go down to useful resources, scroll to the very, very bottom, and you'll find one that says Digital Fabrication Workshop, Rhino file. Now, I've been very kind. Even though I'm using Rhino 8, I've saved this as a Rhino 7 file, just in case anyone at home hasn't upgraded. If anyone here is using an older version of Rhino 7 on a laptop, this will still work on it. Obviously, Rhino 7 files work on Rhino 8 anyway. So I'll give you all a couple of minutes, download that, and open it up in Rhino. Again, I'm just going to give you a couple of minutes. Should end up with 3 things in the file. There's a couple of examples we're going to work through one after another. One with some self-intersections, which is a common problem with 3D print and fabricated components. One with non-manifold edges, which we'll talk about what that means. And then one with completely open objects, which is our most common problem that we face. I'll show you how to fix those as well. Like, see, most of you have got that open. Some of you are still opening it, so that's fine. Give you another minute or so. most likely be a big I'm going to show you how to close later date. So perfect. Right, onwards and upwards, on to the interesting bit. We have a few objects in the file. Each of these objects have issues, and these are the most common issues that I've come across in my many years of 3D printing and 3D modeling things. You don't need to know what these are just yet, I'll explain them as we go. But essentially we've got an object over here. So for instance, you know I showed you that CNC machined relief? That was this object here. We actually stole that from online, believe it or not. Now, at first glance, this looks like a good object. I think we can all agree this looks pretty decent. You know, first glance, I'd say actually the topology looks good, like the way the wireframe's built. I can't see any problems. That looks 3D printable. And I send that job off, and they come back, and they're laughing, and they're like, this just isn't even close to 3D printable. So key issues here, when I look from the underside, firstly I can see it's an open object. So that's something we need to resolve. But this has actually got some hidden issues. So firstly, when I try and select it, I can see this is made of broken pieces. They're not joined up. It's not one big unified thing. So that's something we're going to need to fix. But more importantly, it has an issue called self-intersections. I'm sure it's self-explanatory, but can anyone tell me what a self-intersection is? Or a guess? Exactly, yes. So it's intersecting itself. It's basically turning itself inside out in some places. And what happens in that case is it doesn't know what side you want to print, because it has to be one clean, watertight object to 3D print something, yeah? Whereas if something then goes inside out, inside itself, it's like, is this the inside or is it the outside? I don't know. What do I do? And the machine will glitch and cause errors. And that's why you get a lot of failed parts on the printers. So a few things we can do to fix this. Very first thing I need to do is separate this out into its separate components, because some are joint. Like I can clearly see these aren't joined together, but when I select them, it's coming up as one mesh. So I'm going to select all of these. And I'm going to use the mesh drop down for this. This is mesh geometry. And this section over here where you got repair tools, edit tools, and the booleans, these are so good. Like way better than most other software. There are dedicated 3D file fixing software out there, but generally I find Rhino actually does a better job of fixing them than even they do. So I prefer just fixing stuff directly in Rhino. So much better. So for instance, if I go to mesh repair, or mesh, repair tools, and choose this one, split disjoint mesh, this will split the mesh into its separate pieces if they're not joined up. Split disjoint mesh. So now, for instance, I can select just that end piece, just this one. I can get into its base components. So this makes it much more digestible, especially if I'm doing like a group project, for instance. I can give one piece to one person, another piece to another. Say, you fix this one, you fix that one, you fix that one. In fact, you could all do this between you now if you wanted to, if you want to all choose a piece each. And you could go through, fix each piece, bring them back into one file, and then you could just union them together, make them nice and solid. And you end up with super, super clean geometry. Now, I'm going to click on just one of these. I'm going to choose this top piece up here. And I'm going to type in the command isolate. If you just type in ISO, hit enter, it will come up. Do recommend you do that split disjoint mesh first, so that you can get to just one single piece like I've got. So I've isolated my component. Any joy? Thank you so much. With my component isolated, I'm going to type in the command ZSA, short for zoom selected all. ZSA. So now I've got to a single component, I'm zoomed into it, and now I can start to look at the issues within it, yeah? And I would typically do this one component at a time. Obviously, if you have a file with thousands of components, you wouldn't use this method. This is just for if you're doing something that's high detailed or something that's really important that you really need to get printed. And if you're making a mold or something. Now, looking at what we've got here, this base geometry, I'd say this looks pretty good actually. So who would say this is probably fine? At first glance, I'd say that looks probably fine, right? Now, there's a magic command. If you select the object and type in the command mesh repair. Mesh repair is so good. It's worth mentioning that if you're importing stuff from 3ds Max, SketchUp, Revit, Vectorworks, any of those software, and bringing it into here, you can run mesh repair on it and fix those geometries. Who here uses SketchUp? I still occasionally use SketchUp, I'm sad to admit. If you're importing your SketchUp models, obviously they come in as mesh objects, yeah? Just like this. If you want to convert those to Rhino objects, you can do that. And I will be covering that as part of this whole process we do today. But the most common issue you'll ever find with a SketchUp model is self-intersections. See it all the time. And non-manifold edges. So I've typed in mesh repair. Pops up with this little box. I've got my object selected. And I can just click on check mesh. And this straight away says, this is a bad mesh. Like, oh, well this looked like a good mesh. I'm now very upset. Why is it a bad mesh? So it says, what's wrong with the mesh? It has 34 pairs of faces that intersect each other. So at some point, there are 34 little squares, or 34 pairs of squares, that are basically doing this. They're self-intersecting. They overlap each other. So to make this as a clean model, I need to find where those self-intersections are, remove those faces, rebuild that area. There's a fast way to do it, don't worry. And once I've rebuilt that area, I can then finish closing it, and that can go off for 3D print. That's a finished clean part. So it's actually not too bad. So now I know what the issue is. I know it's a self-intersection. It also says it has naked edges. This just means it has open edges. There's no point closing the open edges until we fix the actual problems first. So, self-intersections. I could have a look around the model. I could try zooming in everywhere and say, well, all the faces look good. I can't see any problems. I can have a look under here, and I mean, eyeballing it, I can see where the problem is straight away. I can see on the underside, that face comes that way, that face goes that way. That's where it's overlapping, yeah? That's where it's doing this. So straight away, I can find it if I manually search. Rather than manually searching, you can just go to Mesh, or Mesh drop down, go to the Repair Tools, and choose this button one. Mesh self-intersect. So Mesh, Repair Tools, Mesh self-intersect. If you're on Rhino 7, you won't have this tool. This is new to Rhino 8. Used to be that you had to like make your own custom C# script or Python script to be able to find self-intersections, unless you're on like a work in progress version. So I've clicked on that. It says select the mesh that will be converted to meshes in memory. Press enter. And once you press enter, you'll see what it's done. In fact, if I do ZSA again, if I zoom to it, you'll see it's found where that self-intersection is. It's actually created a curve that I've got selected. I can see that boundary for my self-intersection. Now what I could do if I really wanted to, I could use that curve to trim both of these meshes, and then they would hopefully just be meeting at that point, and then that would fix it instantly. That's one way to go about it. Now rather than just going to mesh, repair, and mesh trim, I'm actually going to take a more destructive approach. I want to get a bit more control over it. And I'm going to delete some faces manually. So I could either go to Mesh Edit Tools and go to Delete Faces, or I could go to Extract Faces. I'll leave that up for a second. So Mesh, Edit Tools, Extract faces. And where I have that boundary, I can just click along, start removing any faces where those intersections occur. I'll do this on both sides. Hit enter, hit delete, and that starts deleting faces. Do the same thing on this side. Again, doesn't have to be perfect because we're going to rebuild it. Something like that. So that's my own way of kind of trimming this off without breaking any geometry, yeah? I'm going to give you about 30 seconds to quickly do that. So mesh, edit tools, extract, faces. Now the cool thing is you don't need to select every single face. You just need to select those perimeters. Because as soon as you break that, as soon as they become almost separate objects, remember you can use that split disjoint mesh to separate them. You could just delete those floating pieces. So I'll give you a minute.
Would you say that it's actually easier now to manipulate meshes for intersections than it used to be with nerves and random?
Yeah, I'd say so. Yeah, I think there's a lot more you can do with meshes now. I think if you know the main principles of mesh modeling, if you really know how to manipulate them, so much more powerful than nerves. Believe it or not. And I hate to say that because nerves are supposed to be the be all and end all, but meshes. Yeah. I think especially now there's like sub-D tools as well, which technically are a hybrid between nerves and mesh. Yeah, you could do some cool stuff. I'm going to do some cool bits in a minute with this actually. So hopefully everyone's deleted those pieces. You see what I've done. You can see where that curve was before. I've just gone along and I've deleted some faces along that perimeter. Now when I try and select these floating pieces, obviously they're still connected. So I would do the same as before, go to mesh, mesh repair, split disjoint mesh. Or you can start using the commands, just type in split disjoint mesh, it will come up. And you see now I can select these floating pieces and just delete them. So I'll end up with something like that. So I can see now that's definitely not self-intersecting along that edge. I could rotate around and check it. I've got one small self-intersection there that I still need to remove. So I'm going to quickly delete that face. That looks pretty good. What I'd recommend you do is once you finish resolving one self-intersection, delete that curve where it came up with before. You could also just do select curve command and then hit delete just to remove all curves. I'm going to repeat the same process again. So before I go joining these up and fixing them, I'm going to repeat the same process. I'm going to select my object, repair tools, mesh self-intersect. This now tells me 0 intersections were computed. If I go to mesh repair and check it, and click on check mesh, this also tells me there are no self-intersections. Just doesn't mention them. So straight away I've fixed that. All I need to do now is connect this back up and clean it, basically. Now, I've seen people, and I've been guilty of this in the past, manually trying to draw faces in one by one, little triangles, and joining them back together. You don't need to do that. You only need to basically block up the ends of these. So I'll show you what I mean by that. If I use my polyline tool, make sure I have the vertex snap enabled. You need the vertex snap to be able to snap to vertexes on meshes. It's the same as snapping to like an endpoint on a NURBS object. You've got vertexes and knots. So vertex snap is enabled. I'm using polyline. And what I want to do, I just want to basically create a rectangle to join these pieces up. So something like that. It's a bit hard to see. I'll try and do this at an angle. You see I'm connecting this edge to that edge there and back down and across. And once I've made myself a rectangle connecting these pieces, I can go to Mesh, from Closed Polyline, and that will now add in more faces. And that polyline could be as complex as you want it to be. It doesn't have to just be a single triangle or a square. This could be entire boundaries across this if you wanted it to be. And you could fill that in with closed polylines, and it will just create entire new meshes within that you can then still pull around and manipulate. Now, at this point, we're going to talk about some naked edges. So I've obviously just made this little mesh there. I've still got my original one with a gap. Now, if I were to go to Analyze, Edge Tools, and Show Edges, or just type the command Show Edges, we'll say select the object to show the edges, and press Enter. And this will show me naked edges and non-manifold edges. Now we're going to talk about non-manifolds in a minute. Put those out of your mind for now. A naked edge just means that there's an open edge, basically. There's nothing there to keep it closed. So even though I have modeled my extra faces here, I can still see there's a pink edge running along the edge there because I haven't joined it. I'll type in the command join, select both of these together. I no longer get that pink edge, and now I've got a smaller boundary. So this now breaks it up. I've now got two sets of faces that are open. I've got this hole running along up here that runs to that edge, and then I've now got a flat boundary that's open running along here. And I've broken that just by adding in a little square there and joining it. So now I've got two separate holes on two different planes, right? Do you want me to give you a second to catch up to that, or? I know I'm going a bit fast. Again, not a beginner session, this one.
Hold on, is there like a magic command to, right, I know it's about like what, 10 faces back. What if it's like 1,000? You're not going to do the same thing, right?
It depends. In fact, we'll do one with 10,000 faces in a minute, which is the big site model. Because what we'll do, in fact, I'll show it in a minute. What we'll do, we'll add a base to the site model, because that's always good to do. But essentially, yeah, you would. You just do it strategically in a few places, and just to break those kind of groupings of holes, and then you would fill those holes separately after. Gives you more control over how they generate. But for instance, yeah, in fact, a good example, if I try and fill this one in here, if I go to Mesh, Repair Tools, Fill Hole, it says select the edge where the hole boundary is, so I could click on one of these pink edges, and if I'm lucky it will fill it in, but you'll see that for this one up here it's not filling it. No matter how many times I click it, it's not filling. So that can either be because there's self-intersections, or because we need to break this shape up a bit further. So it's usually if it can't work out what faces you want to basically join together. So for instance, I could break this up a bit more, make another rectangle to add that in. Maybe I know I want to connect these. Oh, yeah, I don't like that one. That's not nice. In fact, I might delete a couple more faces here just to line those up a bit nicer. Yeah, be able to join those up a bit nicer. So it's about kind of pairing faces. So I can make a nice rectangle in here, for instance. There you go, that doesn't self-intersect. And again, I'm just repeating that process again and again. So from closed polyline, join those shapes together. And you see it's breaking those up into groups. So once you kind of get used to doing this, you get a feel for where those issues are. So I instantly knew for me it was going to be there, because that's where it kind of changes between different planes. And sometimes it doesn't like filling holes across multiple planes. Whereas now, this is a mostly planar kind of hole. If I were to go to Mesh, Repair, Fill Hole, click on the edge, that now completely fills that entire boundary with polygons. I can try and do the same down here as well. I might still need to delete this face, I'm guessing. Yeah, so it'd be the same thing there. It doesn't like that one. But again, once you get the hang of it, actually really easy to do. So that one, I didn't even need to add a face. Just needed to delete a face to remove it going on a different plane. And then now it's patched that together. It's gone something a bit more like that. Now, for those of you that have worked with SketchUp files before, if you've brought your files into Rhino and if they've looked like this, where it does weird reflections on edges and stuff, you might be familiar with a view like this. That's what we call flipped normals. You know, in SketchUp, you get like slightly different colored faces depending on whether it's an interior or external face. That's essentially what this is doing. It doesn't know whether this is facing inwards or outwards. So what we want to do is rebuild the mesh and tell all of the faces to point in one continuous direction, outwards, effectively. So what I'm going to do is select my mesh, and I always do these three commands in the same order. I'm going to go to the repair tools. I'm going to do rebuild mesh normals, then unify normals. Now, if you're pretty clever with Rhino, if you've got it on your personal device, you can set up like a little hotkey or like a little batch just to run through those. So I can have it on my home machine, for instance. I've got it set so that when I press F1, it does those three in order. It will rebuild the mesh, rebuild the normals, then unify the normals just by pressing F1. And there are ways you can program hotkeys in Rhino. Just type in hotkey, you can do it. Or shortcut, or alias is another command you can do. Alias is another command you can type to set your hotkeys in Rhino. So I'm going to click on rebuild mesh normals, and unify normals. And you'll see now they all look much, much cleaner. Much, much better geometry. Yeah. Just makes them all face in the same direction. So unify, unity. It's pretty unity for normals.
So when you rebuild, what is rebuild? Like, can you just explain those 3 steps?
Yeah, so essentially what it's doing at each step, when I go to repair and go to rebuild mesh, what that's doing is kind of resetting the mesh itself, how it's built. So if everything's been joined together, it will kind of remember that they used to be separate pieces. But when you do rebuild mesh, it'll make that, like basically almost delete the original and rebuild it as a fresh. So it will say each of these vertexes, it will renumber each vertex in order, make them all nice and clean, and it will say that's now one new object, effectively. Rebuilding the normals, again, that's the direction of each face. By rebuilding that again just resets those into their direction. If they're still facing the wrong direction, you then do unify normals. So those directions then all face in one continuous direction. You get a clean object. So it's quite a lot to remember, but really useful when you're trying to troubleshoot a model for 3D print, or even for visualization as well. You know, flip normals is still an issue for rendered projects. So this is also still a fix for that as well. So again, not the most exciting, but knowing how to fix that quite quickly, if you don't have many self-intersections, and there are no self-intersections on this now, this is almost 3D printable. In fact, let's make this 3D printable. I can see I've only got 2 sets of faces left that are open. And if I were to do mesh repair now, I can see I've just got 140 naked edges. Now, do I need to manually draw every single face? God, no. Of course not. Hell no. All I need to do again is find a common edge where those planes change. So we've got this one on the XY plane underneath the object, this one on the XZ plane. And again, all I would do is make a rectangle between those points. Make sure you're snapping to the vertexes, something like that. Bit hard to see in this colour. You see I'm snapping almost like to the grid. And then same commands as we've been doing. So I would go to mesh from closed polyline. That would add 2 faces in to bridge those, but you see we have quite a lot of resolution coming up here. If I were to join that now, that's going to create really messy geometry when I try and fill those holes. In fact, I'll show you what it does, and then I'll show you what I would do to fix it. If I were to join it now, and then just go fill hole, you see it does this. It does this kind of spidering across it. That might be fine. There's actually no problem with that. But if you don't like that, before you join it, you could type in a command called quad remesh. Quad remesh is one of the best commands in Rhino 8. Again, it's brand new to Rhino 8. It didn't work very well in Rhino 7, in the later versions. But quad remesh will let you build any mesh, and it will retopologize it. So for instance, I could type in quad remesh. I could say, okay, make this into 15 quads, 15 faces, and click OK. You might want to delete the input objects to remove the original. And you see what that's done? It's turned those 2 big triangles into a clean, evenly subdivided mesh. Much, much nicer. So now I can join those together. I can fill that hole again. Stupidly, I didn't join it very well. Sometimes it will break on the edges, in which case you might just need to type in points on any vertices that have moved, which I think is this bottom one. Just move it. Something like that. Move it back. And then it should join. Yeah, I think that's okay on that side. I think I just accidentally moved a vertex. Yeah, that's better. See, it's done the same on this edge. Even though I've just typed it to go join, it's still pink. If ever you get that, again, just move the vertexes. Just type in points on. Move a vertex out of the way. Move it back again. It'll fix it. So something like that. There you go. If I join that now, that should be fine. So no pink edges. And at last I can fill that hole. It's obviously still spidered up there, which is fine. But it's now creating a much more optimal form of triangulation. It's now more evenly spread up to that face. Much, much better. Now, one thing that's worth mentioning, just before I go any further with this, what I could do, I could use quad remesh on this entire object. So before I start adding the bottom face and the end face, I could completely quad remesh this to get much better geometry overall. So if I select this, in fact, if I make a copy next to it, I'll show you the difference. If I type in quad remesh, tell it the target number of faces that I want. So maybe I want this to be made from 2,000 polygons. Delete the original object. It's going to do some thinking. It's going to rebuild that geometry, but much, much better geometry. Much better topology. So much cleaner. So again, it's up to you how you want to work.
Why is that not being standard?
What do you mean?
You said it's being rebuilt, it's always like that. Why when you're building it, like initially, is it not meshed?
could be any number of reasons. It could be down to the number of control points in the curve that made this shape. So if this was like a swept object, it looks as though there were quite a few control points in this curve there.
Yeah.
If I didn't reduce the number of control points, that would make for a really dense mesh in that area. Whereas if I just rebuild it afterwards, it does a much cleaner version of it. It's actually kind of ruined that edge a little bit. I'd want to tweak my quad remesh settings a bit to adjust those edges. But yeah, it would just kind of evenly subdivide it, and you get much, much nicer geometry. So yeah, just to stop dragging this one out any longer, because that's more or less the end of self intersections. If I were to just bring that piece over, as we know, I could fill all the holes, go to join, fill that hole, fill the bottom one, and then do my 3 commands. So rebuild mesh, rebuild mesh normals, and then unify the normals. And now I've got a nice clean watertight object. I'm hoping if I go to mesh repair there shouldn't be any problems. So I'm going to click on check mesh. Perfectly clean, pristine mesh. So good mesh, no degenerate faces, no n-gons, no short edges, no non-manifolds, no naked edges, no duplicate faces. That is squeaky clean. I could send this off and that could be a final fabricated part for mass production from an edge. That would never ever have a problem. So again, might be a bit long-winded, but by manually doing those fixes, manually learning what those tools do, how to generate faces, how to quad remesh to get more resolution, things like that, it makes such a difference. Now, one thing that became an issue, I think we can all agree, because we're working on a grey thing, a grey file on a grey background, very difficult sometimes to see what's the inside and what's the outside. And what I like to do personally, this is why I've struggled a bit, because it's not set up the way I usually use it. What I usually do is colour the back faces. So a back face is any face that faces inwards towards an object. And in fact, if I just make a box quickly, I'm just going to extract a face. You don't need to do this, I'm just going to show it to you. So I've got my box. Any outside face of my box, I can have one colour. Any inside face of my box, I can have a different colour. And this means that when I'm working on a very complex model, like with 10,000 faces, I can just orbit around my model and straight away look for vivid colour to see where there are problems. It's a very nice way to visually find problems. So to do that, you go to File and Properties, or type the command Properties. Click on the View drop down right at the bottom of Properties. So just down here, click on View. Click on Display Modes and expand Shaded. So Properties, View, Display Modes, click on Shaded. And on Shaded, you've got this option just here, Back Face Settings. At the moment it says Use Front Face Settings. I don't want that. I want to change the color of my back faces. So I'm going to choose single color for all back faces. Where it says single back face color, that's now appeared. Maybe I want this to be, I don't know, magenta. So I click OK. And you see what that's done now. This makes this so much easier to fix files. Like infinitely easier to fix a file. Because now I can see what's the outside of an object and what's the inside of an object. And if I'm like orbiting around this, I can say that all looks fine. Oh shit. There we go. That's all pink. I know I need to close this boundary. So I find that really, really useful.
Do you remember those faces when I wasn't sure whether it's a back face or front face?
Yeah.
I was going to color those.
Ah, good question. So if I type in show to bring back the original geometry, find another object with some self-intersections. I'm guessing we'll have quite a few. Yep, this one has 30 pairs of faces. Let's have a look at this. If I go to the underside, straight away on the underside, look how easy that is to find those self-intersections. So I can see the pink of this face, I'm seeing the outside coming through from the other face. So straight away I can see the inside and outside of the object.
No, I meant, remember when you tried to build that vertical face and created like really weird 3D and whatever. You know what I mean?
Ah, I see what you're saying. Yeah, so before you do the rebuild. It should still do it normally. It should still look normal, should still be grey, but it's just the reflections would be a bit weird because the normals are a bit off.
Yeah.
But the geometry would be correct. So it'd be slightly different, but yeah, I see what you're saying. That's a good question, though. Right, we don't have much time, so I'm going to move on to the next thing. So that's self-intersections. That is the hardest problem to solve, which is why I wanted to start with that. Not necessarily the most exciting. Next up, we've got non-manifold edges. I'm going to type in show to bring all my objects back. I'm going to go to my second object, which is this cat that's made of like Voronoi. Same thing as before. Looking at this, looking around. I know I've got my back face color on. I'm not seeing any issues, just orbiting around. The geometry actually looks really good. So I'm going to type in mesh repair. Mesh repair is what I always check my stuff with. And click on check mesh. Now this says this is a bad mesh. Oh no, poor cat. What are we going to do? Do we put it down? No, we're going to save it. So this mesh has 2 non-manifold edges, 1 duplicate face. It's got 1 pair of self-intersections. And then 141 faces where the normal differs substantially from the vertex normals. Now that last one, I'll explain what that is later in a minute. You don't need to worry too much about that for 3D print. That's more of a non-issue. So if it says the vertex normals face a different way, ignore that issue for 3D print and fabrication. Doesn't matter. All of the other ones though, like non-manifold edges, duplicate faces, these are problems you would need to fix. And again, these are the most common issues you get from importing SketchUp and Revit geometry. So, one thing we haven't looked at, we obviously looked at manually fixing stuff. After we click on check mesh, you do also have repair mesh and you have next. I'm not going to click on repair mesh straight away, I'm going to click on next. And you'll see that you can actually choose these in order. So it says 1 duplicate face, 2 non-manifold edges. I'm going to try clicking on 1 duplicate face and clicking on repair. Give that 30 seconds or so, that should do some thinking. That duplicate face has now gone to 0. I didn't need to manually go through and find a duplicate. It found it for me, it's deleted that duplicate face. I could do the same thing for non-manifold. It's got 2 non-manifold edges. I can click on that, click on repair, wait a second or 30 seconds. Hopefully it'll remove those. So for me this now says 0 problems. That sounds like it's fixed, yeah? So I click on finish. Well, I'm going to recheck it straight away. So I'm going to select the cat again, click on check mesh. And in fairness, that has fixed it. If it hasn't fixed it, you would need to manually find those objects and delete them. In which case, you'll find them under the mesh repair tools. So for instance, you've got, it might be under the edit tools, sorry. Should be one for duplicate faces, merging faces, deleting faces, cold degenerate faces. Any of those issues that come up in mesh repair, you can find most of the solutions in the mesh repair tools. So just use those, work through the process, delete the faces, rebuild those areas. So that looks pretty good to me. That says I've got 140 faces where the vertex normal differs substantially from the vertex normal. Doesn't necessarily mean the mesh is bad. It can be a problem if it's for rendering or booleaning purposes. I'm not doing either of those things. I'm 3D printing it. So for me, that's a fixed file. That's done. Now, some of you might be thinking, so what the hell was a non-manifold edge, Jay? What was that about? Non-manifold edges are this. So if I just copy and paste an object, typically non-manifold edges will occur when you try and merge objects that share a single edge. So remember we were having those self-intersections? It didn't know which side was inside and outside. This is very similar to a self-intersection, but this time they don't overlap, they touch perfectly. So for instance, should that edge there be shared between these faces, or should it be shared between those faces? Does this face actually attach to that face? And does that face attach to that face? It doesn't know how to handle that. That's what we call non-manifold. So an easy way to solve a non-manifold would just be to create a slight overlap, ideally. I might now be creating some problems just here, because again, they share the same face, but we're going to see what it does. By unioning those, that would generally eliminate non-manifold edges. Because now this edge is separate to this edge, because there's distance between them. So that's generally how you would resolve a non-manifold edge. Now we've got about 20 minutes left. I'm going to move on to a site model now. So who here has followed my YouTube video, Ultimate Guide to Site Modeling? Some of you. I'm shocked to find it's actually just hit 10,000 views in the last 2 years. I'm quite proud of that. Bearing in mind it's like an unlisted video and it's still hit 10,000 views. I'm now thinking I need to start cashing in on this, make some good videos. But if you follow that tutorial, it shows you how to use Digimap data to build a 3D terrain, and then how to basically get all the 3D buildings in, vector-based maps, all sorts of stuff. In fact, if I write this on rendered view, you'll see how pretty this one is. See, we've got a little vector map on there, or raster map attached to the surface. Quite a nice little model, I think we can all agree. Now, what if I wanted to make a physical model of this? You know, at the moment, we can already now identify what some of these issues are. So for instance, I can select this terrain up in my command line or in properties. I can see this. Why can't I do my magic thing? I can't do my zoomy thing. Hey, I can see up here in the command line it says it's one open mesh. Well, we know that for 3D printed and CNC'd objects, whether I want to mill this or 3D print it, this needs to be a closed, watertight object with no problems, yeah? So I think I'm going to fix that first. I'm going to fix the terrain first, because this answers your question a minute ago. Now, a couple of ways to go about this. If this were a surface or a solid, obviously you could do what I did in the video. You can extrude that surface down, make a box underneath it to subtract it, give it a flat base. You've got a 3D printable object, yeah? A solid watertight object. With a complex mesh like this, it gets a little bit more in depth. So what we can do, I'm actually going to view this in the top view, just up here. I'm going to select my terrain, just the terrain. But what I want to do, I want to make an outline of this mesh. So I'm going to go to curve, curve from objects, mesh outline, or I could just type the command mesh outline.
How's it different from duplicate border?
So duplicate border will generally work if it's relatively close together. What I found on this, because I tried using duplicate border on this morning, when you go to edit, extract, whole boundary, which is the same as duplicate border, when you click on the edge, it should generate a curve around. It's not doing it for some reason. So it's a little bit annoying. So instead, what I'm doing, I'm just doing it in top view, because I want it planar anyway. Doing it in top view, going to mesh outline, and as long as you're looking straight down at it, it will do a perfect outline of that mesh.
Why would it not do it?
It's a good question. It should do it, but for some reason on this particular file I have, it doesn't do it. But mesh outline will always work. The interesting thing with mesh outline is it's view dependent. So for instance, if I select this Voronoi cat thing that I got, go to mesh outline again, I've done that in my right view. In fairness, that's the most complex object I could have chosen, because it's all the Voronoi stuff. There we go. That is now created. It's almost like a make 2D that's view dependent of the mesh. And it will move it all onto one flat plane as well. So there we go. So I've got my hole boundary. Now the cool thing with that hole boundary, if I just full screen that a minute, it places control points for that curve in the exact same places of the mesh that we extracted it from, yeah? All those vertices line up, even though that curve is flat, it's planar. So I can now move my curve down below my model, something like this. Yeah, something like that works pretty well. And then to make a base, just go to Mesh from Closed Polyline. And that gives me a nice flat mesh base. Now if I'm not happy with the topology of this, obviously I could just do a quad remesh. So maybe 2000 might not be big enough. But straight away I can get a nice flat mesh that matches the dimensions of my model. Now I'm actually not going to quad remesh it because I want to match the vertices on this. I could quad remesh it later if I want to. But the great thing I've got with this, if I now want to connect my curvy contoured surface, my big mesh surface, my terrain, if I want to connect that to a mesh base, a flat one, just draw a rectangle, same as we did before when solving the self-intersections. Draw a rectangle there. From closed polyline, join them together. Now notice that pink one is inside out at the minute. It's facing the wrong direction. I would need to use rebuild and unify normals to orient those the correct way. That's fine. I'm going to do the same thing on the other side. I'm already aware that that face is an issue, but I can solve it later. Draw a rectangle on this side. From closed polyline, join those together. So now I've got a closed boundary on a single plane. That means I can now fill that, yeah? That entire face along there, I should be able to now build. So let's do the usual fixing. Rebuild mesh normals, unify normals. Now that's corrected the directions. It's actually pink on the inside up there, pink at the bottom, pink on the inside face there. So all those face orientations are correct. Go to repair and fill hole. Select the mesh edge if I can find it. Might have to click a few times. And now that's completely filled in. And again, I just need to do that one more time on the back. Once I do those two back corners, I can then fill all three sides there. And that is one completely clean, closed model, no self-intersections, ready to 3D print. Or CNC. All I would need to do is scale it down to the correct scale and chop it up. So, definitely something worth doing that. I'm not going to bother fixing the rest of that. It's kind of self-explanatory how to fix those last three edges. Just repeat what I just did for the other three. You get a closed object. Another thing that's worth doing as well sometimes is cleaning up the geometry here. So for instance, if I wanted to work with a surface, the other part of my video I did on YouTube was generating a surface terrain rather than a mesh one. So what I might want to do is actually convert all of my buildings to solids. This is the bit where I'll show you how to convert SketchUp and Revit models to Rhino clean geometry. So a good way to do this, select all of the meshes. I've got them all on a layer. I can open this open object layer, right click the building layer and just do select objects. I can select all of my buildings in one go. I'm going to type in the command mesh to NURB. I'm going to turn my mesh object into a NURB object. I've got a load of mesh objects there. Let's go do a bit of thinking. But that's done it already for me. And then what I should end up with, I've got mesh objects in the same place, but I've also got NURBS objects in the same place. So if I go to Edit, Select Objects, and Poly Surfaces, you'll see I've got those in the same place. So I'm just going to isolate those for a minute. I don't want to select the mesh versions, I only want the poly surface versions. And that gets me all of those objects, all those meshes as poly surfaces. Now again, I'm sure you're thinking, well, Jay, that still don't look good, mate. That still looks like meshes. It's still all triangulated. And that's where I say, there's a technique. So this is where I can select my objects like this one. That's a particularly heavy one, I think we can all agree. And there's a command. If I start typing in merge, it's quite a long command. Merge all coplanar faces. So planar obviously being flat. Oh, it looks like a perfect solid object that I modeled in Rhino, despite it originally being a mesh. So let's say, for instance, I wanted to now render with that. Firstly, that's a much lighter file as a solid because it's clean geometry. So only using the border NURBS to create this. If I wanted to do some analysis on this in, say, Ladybug, and if it doesn't accept mesh geometry, I can now convert it into a solid and use that in Ladybug for environmental analysis. But most importantly, if I'm working with a solid terrain, I can now subtract a solid object from my solid terrain to make a foundation for the building to sit in. Just by going to solid and different, just subtract it. 3D print my little buildings and they'll now fit in. So it's great. So useful. And you can select all of those and do merge all coplanar faces for all of them. You don't have to do them one by one. That's just going to run through and do all of those. Oh, also for Make 2D, when you're doing diagrams of big site models, clean them up like this first, just to get them as clean outlines rather than triangulated. Make 2D, and you get perfect diagrams of all the building outlines. It's another cool thing you can do with it. So that's going to do some thinking for a sec.
So you're not a big fan of view capture to file?
No, I quite like view capture to file, but if you're doing it the right way. So view capture to file it. If I'm doing like a render or like a shadow study, I'll do view capture to file to capture that. But then I'd also do make 2D to get the vectors, lay it on top, and bang, there's two. Get such a better result. But yeah, view capture to file is great. So much better than a screenshot at least. Still see people submitting screenshots. Just yeah. Yes. Say that again. It's a bit of a mouthful, the command. It might do some thinking. There we go. Mine's done some thinking. Wow. Look how clean that is. That is seriously clean. So much better. So if I was to do a make 2D of that now and put it into Illustrator, line weighting that is going to be a breeze. So easy. Much better to work with. Especially if you compare it to the original. If I just move this out the way for a sec and type in show. I moved it the wrong side. If I move that over this side, so original geometry being all like this, all triangulated and nasty. Rebuilt geometry being all clean like that. Again, so much better for 3D printing, CNC, because it doesn't need to calculate all of those polygons. It's now just reading edges. So much better. Now, I am aware we've only got around 8 minutes or so. We don't have long left of the session, so I'm going to try and finish at 4 on the dot if I can. The only other thing that's worth mentioning is obviously laser cut files from these. The most common laser cut models you would be making are either going to be exploded models. So for instance, now we've cleaned these up, I could simply explode these, just type in explode. That gets these into single faces that I could then just lay flat and laser cut those outlines. Just do a make 2D once you've laid them flat. That gets you all of the outlines, lay them out on a sheet, that's your laser cut files that you can then merge together. You might obviously need to trim off edges if you're using a thick material, like just to make sure they don't overlap or anything nasty. If it's something like cardstock, you typically won't need to. Just explode, lay flat, make 2D to get the curves, and then you've got yourself some vectors to lay out onto a sheet. The only ones that then get a bit confusing are working with contour models. So you remember back on that presentation, right near the beginning, on page 4, we had this like topographic model where it's like the layered model. Super easy way to do that would simply just be to use the contour tool. So for instance, if I make a plane, I'm just going to add a bit of resolution into this plane by typing in rebuild, change a few values. Again, you don't need to do this bit, I'm just going to show it though. If I just select a few points, make something a bit organic, like it could be a terrain. Beautiful. Look at that. Oh, I could be the next Zaha Hadid. What do you reckon? Something like that. That could be really interesting. So trying to turn that into like a laser cut contour model of like a terrain or hill or landscape or something, I'd need to go through the same process of what we did in a mesh. But the faster way to do it, if you're working with a solid or surface, just extrude that surface straight. Make a box over it. Something like that should do the job, methinks. Then go to solid and difference. So select the thing to subtract from, thing to subtract, and that gets me this solid object. So again, I could 3D print that one or CNC it because that's a closed poly surface. There's no issues. Worth mentioning as well, before I convert this into a laser cut one, if you're working with solids, obviously to send stuff to 3D print or CNC, you would export them as an STL file, as we mentioned on the presentation. If I go to File and Export now as an STL, it might come up with some issues. It might make a really heavy file that's hundreds of megabytes. Probably not for this, but for a more complex model. If I want to get more control over that, I can simply go to the Mesh drop-down and choose From NURBS Object. And I get some more controls here. So I can adjust the number of polygons. I can adjust effectively the sub-D resolution. I can also click on detailed controls to specify like the actual dimensions. So how long do I want edges of polygons to be? Is there a maximum, a minimum? For instance, if this is making a really dense model, but if you're printing to low resolution, like 0.1, set your tolerances as 0.1. You're never going to end up with extra resolution that you don't need. It will make your files faster and more optimal. So I can click OK. That gets me a clean mesh. And if I export a mesh object as an STL, it will keep the same topology as it already has. It won't rebuild it again. Whereas if I were to export that now as an STL and import it back in, it might be a bit janky, is the term. So, contour. Key thing I need to know with this is how big is my object. I'm going to go to Analyze and Distance. At the moment, I can see that this is massive, the one that I've made. 223 meters, this is at the minute. So obviously too big to fit on a laser cutter, realistically. Now if you imagine the laser cutter bed down at B15 is 810 by 450. Well, that's not right. Let's try that again. 810 by 450. I need to fit my big model there onto this tiny rectangle down in there. So I could do some math and calculate it, but I'm too lazy for that and I don't have the time. I'm just going to scale this down by a factor of 1,000 and hope for the best. I'm going to type in scale. 1 divided by 1,000 would be 0.001. Is that 1,000 or is it 0,001? Let's try that one. I'm going to find a scale factor that's appropriate for my fabrication method. So for instance, this one at 1 to 1,000, that would fit nicely on the laser cutter bed, especially if I'm chopping this into multiple layers and laying it out onto the same sheet. So I've got my scale, I've scaled it down. Now that I know my dimensions, I would now need to decide on my material thickness, because that's going to be the distance of my contours. So if I'm using 3mm thick card, for instance, I would type in contour, specify a beginning, which would be the bottom of the model, set the direction, which would be towards the top of the model. The distance between contours would be the thickness of the material I'm going to laser cut. So if I'm doing 3mm card, I'll type in 3, hit enter, and that will generate all of my contour curves as closed boundaries. What I need to do then is lay those curves out onto my sheet, onto my rectangle, 810 by 450, and then I can set those to a laser cut. Colour them red, give them to Scott, give them to Pete, they'll be laser cut. I just stack them on top of each other. And that could be as complex as you want it to be. Again, if I wanted a more detailed one, that just means I need to use thinner material at that scale. So if I set my distance as 1, that gives me even more contours. Annoyingly, it's breaking a little bit for some reason. It shouldn't be. Might be an issue with the file. It gives you these nice clean contours. Just going to remove open curves from there for a minute. And finally, if I want to preview what this model is going to look like, I could select those closed curves, go to solid and extrude the curves, extrude them by the distance of the material thickness, so 1. I end up with something like this. So my laser cut model would look something a bit like that. Now I obviously deleted a couple of layers in there, just because I can't bother to take the time to fix it right now. But I would just rejoin those back up and fix them. And that's it. That's how you prep your files for laser cut. That's how you prep pretty much any file for 3D print. How you fix any file. It's how you fix them for visualization. Might not be the most flashiest or exciting of workshops, but with that knowledge, go into a company, they will pay you mega money for that knowledge. I don't get paid that at this university. I get paid similar to that externally. So seriously, make sure you practice those skills. So game changing. Any questions before I wrap up? Was everyone a bit exhausted? It is a bit of a slow burn workshop. Useful info, but it is a slow burn workshop. I'm going to leave it there then. Thanks.